Alright, so today we're studying two-dimensional vectors. And because I forgot to start recording, so the students are going to hear this again. So when we've already studied vectors in Accelerated 2 when we were working on our milestone, and we were, real quick, partitioning a line segment. So if you look at the notes, we go back over a partitioning a line segment question. But today we're going to actually just look at everything in terms of vectors. So if we have a length and a direction, a magnitude and a direction, we can describe that with a vector. And this is one of the forms that we can describe a vector in. This is component form. The first component is our horizontal move. The second component is our vertical move. So since a vector describes a magnitude and a direction, we can have equivalent vectors. So equivalent vectors would just have the same length and be in the same direction. Do you see here I have two? Those are equivalent vectors. They are the same exact length. And how do I know that? Because I chose to copy and paste them. Okay? So that is a really easy way for me to make equivalent vectors. So I took the same thing and I've pasted it. So they're all the same length. They're all pointing the same direction.
Yeah, okay, this bothers me, but it says equivalent vectors.
You want all the letters in there?
It sounded right.
It just says equivalent.
Which one is it actually? Is it equivalent?
Wait, that's how it's supposed to be spelled.
Thank you.
Equivalent.
I spelled it out. No, I didn't. I spelled it right.
Equivalent.
Alright, I've been mixing up my letters all day long today, so if you see something else, it wouldn't surprise me. Do point it out though, thank you.
Okay.
So, equivalent vectors have the same length and they are oriented in the same direction. Now, with our component form, we can always find component form from going from one point to another by doing the difference in our x's and the difference in our y's. If we let x1, y1 represent our initial point, and a lot of times that initial point is coming from the origin, not always, and then we let the terminal point be represented by x2, y2, what do we have to do to this first point to get to the second? Well, it's pretty simple. You can find the difference in your x's and the difference in your y's. Okay, so if we had, let me erase your try. We'll change it out.
If you divide them, you get slow.
Okay, so if we had point P and point Q, and we're looking at vector PQ, do you see how this notation represents a vector? So it's PQ with the arrow over it, and that is also what we use in Accelerated 2. What do we do to go from P to Q? So this is P, this is Q. Well, this move would be the terminal x minus the initial x, the terminal y minus the initial y. Or you could think of it opposite. What do I do to 2 to get to 5? I add 3. What do I do to -1 to get to 3? I add 4. Because just subtraction is the inverse operation of addition, right? So you can think of it either way. So the vector PQ is represented by this component vector, 3, 4. Yeah, just vectors.
Come on, why do you think it's useful?
We're gonna take a graph. Like I didn't ask you.
Okay.
Why didn't I first
Leave.
Alright, so if we have R is the point, -4, 2, and S is the point, -1, 6, I would like you to find vector RS, please.
Gotcha.
So that my initial point would be R, my terminal point would be S because of the way I ordered it here, vector RS.
It's actually
-3. -3. This is 3.
It's
going
minus
oh.
-4,
Yeah.
that's plus 3.
Yeah, my bad. I did it wrong.
You guys can find
5, 6,
7, 8.
9, 10.
Do y'all want to work on your dance moves in detention? No? Alright, so this is 3, 4. Oh, this is 3, 4.
Hey.
So what do we know about PQ and RS?
They're close.
They're equivalent.
Did you do that on purpose?
Equivalent, yes I did. They're equivalent vectors. Okay. Alright, now we said vectors have two things. They have a length and they have a direction. Okay, so our word for length is magnitude. Now, if I look at this, this is vector PQ. We went over 3 and up 4. What does this make, folks?
A right
A
triangle.
right triangle. So if I'm trying to find this length, PQ, it's Pythagorean theorem, isn't it? Or if you remember, when we proved the distance formula, it came straight from the Pythagorean theorem. This distance A right here, wasn't that just the difference in our x's? And this distance B here, wasn't that just the difference in our y's? Yes. So, to find the magnitude of a vector, all you have to do is the square root of a squared plus b squared. Because A is that difference. B is that difference. So if we have vector V is equal to A comma B, then the magnitude, the absolute value of vector V, which represents the magnitude, is the square root of A squared plus B squared. Okay? Alright, so what would the magnitude of RS be? 5.
Oh,
It would be
5, yeah.
It would be 5.
17, 30,
So, if I gave you these two new points, I would like you to 1, find vector xy, and 2, find the magnitude of that vector.
Okay.
Okay? So this is you try.
Swag, man. Swag.
Can you give us a little bit of time?
Yeah, I sure will. Let's not shout it out, please.
Wait, so how do you write the magnitude of?
It's just a number, because it's a length.
Do you write it out like next to your vector?
I will show you in just a second.
It's 2 on the root of 2. Boom, 2 root 2.
Alright, so if we let V represent this vector, then the vector would be -2, -2. Did you get that?
Technically, yes.
And then the magnitude of vector V, so the absolute value bars represent magnitude, would be the square root of -2 squared plus -2 squared, which is the square root of 8. You're welcome to leave it like that. This is where we've simplified the radical 2 roots of 2. Okay, you're going to notice a lot of U's and a lot of V's. U's and V's are used often when we're talking about vectors. You can.
My U looks like those 2 letters.
Yeah, that's really confusing. They look exactly
I know.
the
Why
same.
do we use
Why I
it?
write is-
Okay. You might find it. Just make sure you put a tail on your U.
It's like a double V.
Same with the A.
No,
Like a
no.
double U?
You're just gonna have to have nicer handwriting, and that won't be terrible for some of you to practice. All right. So let's move on. Okay. Vector addition. Vector addition we already know because we actually did it when we didn't know what we were doing. So to add 2 vectors, if we said vector U is represented by U1, U2, and vector V is represented by V1, V2, then the addition of U and V is just where we add the horizontal components and we add the vertical components. Okay, now the cool part is if green represents vector U and pink represents vector V, when we add these 2 together, it gives us the blue. u plus v. It's our direct path.
So you don't have to do any like tagging to
Distance one.
Okay, so this tells us direction.
Oh.
We're still not, this is not length. Now, scalar multiplication, we've also already done. Because when we partitioned a segment, we multiplied through by a fraction.
This is a lot for us.
Actually, this isn't that bad. I thought it was better.
Okay, I agree with both of you. It is a lot, but what we're learning is not that bad because we really kind of did everything we've done so far in Accelerated 2. We just didn't use the proper terminology.
Even if you don't remember,
I agree
it's
with
still
that.
really
Like, it's
easy.
just that.
Yeah. Yeah, it's a lot of terminology to be thrown at you at one day.
I can tell when to mix up the U's and V's already.
Well,
honestly.
Most of the time, that's okay because we won't be using U's and V's. We'll be using actual numbers. Okay? Okay, so vector addition, just add up your horizontal components, add up your vertical components. Scalar multiplication, you're just multiplying through by scalar. Okay, and what that would do is it would take a little vector, and if we multiplied it by 3, then it would just make it 3 times as long. So it would just grow. Oh, wrong color. I was going to do 1 3 times as long.
I'm gonna do pink, right?
1, 2, 3. There we go. It just grows. Okay, so that would be like if we multiplied by 3. Okay. All right, now, okay, this is where you're going to get a little wigged out. I'll go ahead and tell you. But this is how we can tie it back into what we've been doing. Okay, what we're going to talk about now is a unit vector. And that might be why we're headed this way.
Wait.
I can keep my mouth.
Okay? Because we can think of vectors as direction. We also know about an angular direction, don't we?
We do.
And we know how we can tie that into sine and cosine, right?
You got everything plugged
So, yeah, it's so cool how everything comes back together. But, at times we will need to work with a unit vector. So, the unit vector u is where we take a vector and divide it by its magnitude. And that is the unit vector in direction of vector v.
Why'd you mention it? With the.
Why I gave it a tail up top, because second period didn't like the differentiation between my u's and v's. So we were just trying to
So it's just a
add,
regular V.
it's just a v.
Which was the next one, a U or a V? That's
Okay, this is a v, this is a
We
v.
just use different letters for the purpose of this.
No, come on. Stop making everything difficult.
We should use W.
All right, I'm gonna keep using u's and v's. Y'all do whatever you want.
Let's use M and W. That'd be so easy. Why not X and Y? Oh yeah, why can't you use X and Y?
Okay, so a unit vector gives us a way to represent the direction of any non-zero vector. Okay, so any vector with the direction of v is a scalar multiple of the unit vector. Huh? What is what? This is a U, V, V. This is a V. That's a V. Alright, so if we were to find the unit vector of this vector. Okay, to do the unit vector, we do the vector over the magnitude. So we got to find the magnitude. What is the magnitude of vector V? It is the square root of...
Root 13.
Very good.
Root 13.
Very good. Okay, so it's the square root of 13. Now, I talked about vector addition and I talked about scalar multiplication. So we didn't really talk about division. So could I think of this as vector v times 1 over this? Yes, I could.
That's a yes.
So let's think of this as scalar multiplication by 1 over root 13, and our vector v is negative 3, 2. So this would give us a unit vector of negative 3 over root 13, 2 over root 13.
Wow.
You just multiply.
You lost me at
You just multiply.
Okay, so this is the same direction when the vector has a magnitude of 1. Why would a magnitude of 1 eventually be important?
direction. Sine cos 10.
When 1 comes from a
No!
Yes! It does. 1 ties us back to our unit circle, doesn't it? Because what's the radius of the unit circle?
himself.
1.
Are we doing projection?
Okay?
Colin
We are going to look at our word problem tomorrow. Today is very basic.
How many circles do you have for training?
Alright. So,
Honestly, are you
here
doing
comes
circles?
angles. Alright, so, since we said this, it can all tie back in. Well, it's time to tie it in. Now, no. Alright, so, hold on. I revealed too much.
You did.
I did. I revealed too much.
Oh, it's just cos.
Yeah.
You're gonna learn in one day.
Okay. So,
Too much stuff.
I revealed too much. So here's vector v. Vector v. Now, if I can think of this like I did with the unit circle, this horizontal component would be represented by what? Cosine.
Why did I say X first?
The vertical component would be represented by what? Sine.
Theta.
Now, if this were, if it were a unit vector, we'd be done. But if this vector is not just one unit, then we would have to take this cosine and multiply by the magnitude. We would have to take the sine and multiply by the magnitude. Okay? So if it were just a unit vector, all we need is sine and cosine.
Just take cosine of that and then multiply it.
All right. So how could this be helpful? All right, now let's do a separate example. And I'm picking something we know from the unit circle. Let's say this were a 60-degree angle. We could pick an angle that's not from the unit circle, and then we just use our calculators, right?
Sure.
Yeah, we could. We sure could. No, I wouldn't be in circle. Okay, so if this were our angle here, from the positive x-axis, we had 60s. And this vector, v, had a magnitude of 6. Let's find the component for this vector, the component form of this vector. Okay, so I gave you the magnitude. That's pretty easy. We can plug it in.
6 times cosine.
So it's 6 times cosine of 60 degrees. And then 6 times sine of 60 degrees. So what would the component form for this vector be?
6 times 1/2.
It would be 6 times 1/2 and 6 times root 3 over 2. So this would be 3 comma 3 root 3.
Simple when you have the unit vector, but if you don't, then what do you do?
I have a question.
Sine.
It's kind of off topic though. You know special right triangles 30, 60,
Yeah, that's
90,
the-
45,
yeah.
45, 90? Does that have anything to do with the unit circle?
That's how we created the unit circle.
No.
Yep, that is. Okay. Yes.
Finish,
Yes.
right?
All right. Oh, we are so close to done.
Oh,
We are so close. Okay. Last thing I want to talk about today is component form is not our only form for a vector. A vector can be also written as a linear combination. All right. So this is pretty simple. We're used to working with this. This is what we worked with in Accelerated 2. But let's take a look at 2 special unit vectors And these are named I and J. I represents the unit vector 1, 0.
I cried.
And J represents the unit vector 0, 1. Okay, so I'm going to make this develop on its own. So if we had any vector, and I can represent any vector with AB, could I rewrite this as A0 plus 0B?
I mean, yeah, but that's like why though?
Oh, because I'm trying to get here.
Like,
I don't know.
Alright,
It's
now,
already there.
could I rewrite this as A times 1, 0 and B times 0, 1?
I mean, you could, but
You
it's
could.
Still
Now, if we define I as the special unit vector 1, 0,
AI.
then this is AI
That's BJ.
and this is BJ.
Oh, I.
Julian.
What are you laughing at?
Stop, Julian. I am amazed when it's said. Wow.
Alright,
I just realized where he was going. Like, what are you talking
I have a mic
okay, and that is it for today.
Wait,
And then we have one more.
you're still recording?
Okay? Let me,